Hello, everybody. So, got a few things to go over today. To continue where we were last week. Some more stuff about logic, but this time logic as it directly applies to what we'll be doing when programming. So, instead of the general overview like we saw last week, we'll take that a step further specifically for our purposes, along with at least an introduction to what truth tables are. It's a powerful tool when we get to complicated situations, especially in the electrical engineering perspective, like actually constructing the hardware. But those truth tables are huge. Like if we wrote in like print size font, one of those truth tables would fill up my board. We're not going to do that. We're going to do some small introductions and just go over the concept of what a truth table is, because it scales up very obviously. And talk about our logical operators and logic gates, which will tremendously expand what we can do with selection structures. And then we'll get into modularization. So a few things to talk about today. The first thing I wanted to talk about, or to lead into this, is a logic gate in particular. We're going to talk about it as far as the theoretical concepts of what it is, but I wanted to make sure and show this. When we're referring to logic gate, what we're talking about are little chips like this. So this is 74HC 04, which is a NOT gate. But if we just look at it, it looks almost identical to the 7408, which is a AND gate, or the 74HC032, which is an OR gate. So usually when we use the word logic gate, we're referring to these integrated circuits that all kind of look the same, the little black plastic, and the actual components inside there are very, very small. They make the bigger case so that it's big enough that we can work with our hands, but you can see as I'm holding that, that's just barely big enough to work with the hands. They also make them in sizes that are way too small to work with our hands. Usually when we do circuit boards and that sort of stuff, we draw out the design and then the machine makes the part because it's way too small for human hands. But in general, when we say logic gate, we're talking about the physical integrated circuit, like those. But there's also a conceptual aspect where we'll kind of use them that relates directly to our logical operators, which is the content for today.
So those physical hardware components actually stand, like they're the words that we put in, like basically one's an and one's an or?
Yes. I'm going to draw the electrical circuit up here.
Cool.
Yeah. Okay. Yeah, so this 74HC08, this is actually 3 AND gates. So let me get my orientation. Okay, so this first pin, that's where the power goes in. But then the second 2 pins, we hook wires to those. So the second and third one there get 2 inputs, and then the one next to it would be the output from those 2 pins being ANDed together, which is a binary signal, so it's either on or off. So it does build up.
I can visualize that.
Did that answer your question, Tyler?
Yeah, it did greatly. I'm thinking about how we programmed the wires in the Raspberry Pis, and I'm putting that, like imagining it that way.
Okay, let me flip over.
Hooking that up to a GPIO, you know?
In my notes, there's probably going to be some questions for that, because we have you can see the description, and then the truth table, and then
okay.
a picture.
Literally okay.
Actually show nice. What these are.
Okay.
Hopefully that'll answer some of the questions.
Yes.
Because they're not big, mysterious, strange, super complicated pieces. You actually have every one of these in your house right now. I can just about guarantee you that every house in America already has an AND gate and an OR gate, and maybe a NOT gate. The NOT gate is usually unintentional in a house, but we end up with them. But jumping into this, so logical operators or logical operations, logic gates, and truth tables. A long title up here. Logical operations. I'm just going to put that through the title, but in my notes, I also have logic gates and truth tables. They go together, so it just made sense to go ahead and talk about all of them at once. So last week we discussed the meaning of formal logic, how it applies to across the board, right? In our math class and our philosophy class and all those other courses at college you'll take where you hear that word used over and over again. The basic is a premise leads to a conclusion, and the premise holds a definitive truth value. It's a fact about our situation. True or false is how we would normally state that in formal places, but when we're breaking it down and thinking about it, it can be a lot more effective to just think yes and no, because those are words that we use in normal everyday English to help us organize our thoughts, especially when we get to complicated situations. The premise is a simple conditional fact about the situation. So we have binary states, because that fact is it's either a true fact or a false fact. Not necessarily that one is bad and the other is good. You don't want to apply quality to true and false, right? The example that always springs to mind for me is if somebody says you owe them money and you don't, in that case, false is a good one. So there's no true and false have no inherent quality to them. They're just opposing states. And with at least binary values and some operations, we can build up an entire mathematical system. We already saw that when our coverage of binary finally got up to the 2's complement that machines actually do. And then we have one circuit that we can pass things through to both add or add the negative and build up all our math from that. And in 1847, long before the days of computers, a man by the name of George Boole developed an entire formal system of mathematics using just the 2 values, a binary system. So when we're working with computers now, our binary data type gets named after it. We call those Booleans. So we've seen like integers and floats, or short for floating point number, where we store either whole numbers or numbers that have a fractional component as well, for integers and floats respectively. We've also seen strings and characters. We're kind of treating them together, but technically character would be one symbol, but that's really not enough to do anything with. So when we put lots of characters together, then we get a string, which represents sort of our written language, our standard outputs so far. So next data type to add to that is Boolean, where we directly store the true or false value. And we have those simple conditions, those premises, and we can perform, we can have operations that we can perform on those simple premises that are either true or false to build up more complex conditions to deal with complicated situations. Again, those words I'm using them as complex means lots of simple parts, whereas complicated means hard. So machines can't do complicated things. Machines can only do complex things, but we can do build up enough simple steps to solve hard problems. So our logical operations are going to be not, and or. And for the most part, they fit right with how we use them in the English language. Not something, well, we're in binary states, so not something's even easier. Is we either have a 0 or a 1. So not 0 has to be 1, or vice versa. Not 1 has to be a 0. And when I'm doing, there's already a question kind of pop up. This is another one that's going to relate to microcontrollers and SBCs. Whenever I'm doing port manipulation on those, which is almost working in binary, it's instead of writing a bunch of complicated high-level code, it's direct control over what the bits in each register are. Whenever I'm putting that together, when I assign something to put a bit in one of the registers, I actually think 1 or not 1. I don't ever think about a 0. It helps with an organization thing. So it's almost like our binary state isn't even 2 different things. It's that thing or not that thing. So if you're heading down a pathway that would see a lot of binary, keep that in mind, that the not operation actually leads to a better way of understanding the binary, because we don't have 2 separate things. We have one thing, or we don't have that thing, and that's our 2 states. That's our 3 operations. 3 basic operations. Is not. Oh, that's supposed to be a capital P. And or. And as far as putting the notes together here, when I'm referring to the logical operators, I'm going to at least try to stick with capitalization, because as I was putting my notes together, I kept finding it. I kept encountering the words and or showing up there as well. So when I write and in lowercase letters, that's the normal English, means both of these things. And capital letters are going to refer to our operations, or maybe some symbols. And then we can combine these further. Can be combined. So that like a not, I'm gonna say with. Not with an and produces not and or nan. How we usually say that. Similar thing for a nor, not or. We just combine. It happens so often we combine it into one thing and just say nor. And then we can combine the complex ones. So a NAND gate with an OR gate produces XOR or exclusive OR, which means one or the other, but not both. We'll come back to that whenever we talk more about these.
NAND seems kind of confusing because that's also like a file system type, right?
What, NAND?
NAND.
It's one of our most common electrical systems. The file system's named after it.
Oh, okay, that makes sense. Okay.
So Texas Instruments stuff, like these 3 chips that I just pulled out here, these ICs made by Texas Instruments. Texas Instruments stuff is a step above all of the others as far as durability and longevity, because we can combine these in different ways, and they only use NAND gates. They use NAND gates to build up everything, which gets is getting into complicated electrical circuits, but that's a very, when I draw pictures here in a minute, that is the most reliable type. So Texas Instruments builds everything from NAND gates, which makes their chips more durable, longer lasting, and things like that.
That's why you can like pick up a calculator from TI and it'll still work like 50 years later.
Yes, yes.
Besides the battery replacement, of course, but you know, the chipset will definitely work.
Yes, yeah. Whereas most other makers use all of them. They use these, and then the different combinations, they include those as well. Texas Instruments uses the one type to build up an equivalent to all the others, which is both a simplification and a complication at the same time. but that's an electrical engineering thing.
It just becomes more and more complicated, but not more complex.
Yes. Yes. It makes the diagram, the wiring diagrams form an awful mess. But as far as simplicity, it kind of goes pretty well. So that's our three basic operations, and we can combine them. And I wanted to try to put all three pictures on the board, so it's okay if I go ahead and erase these two initial notes. The basic idea is not an and an or, and we build up the others from there. We'll come back and talk about XOR in a moment. Nobody said no, so I'm going to clear this out so I can try to get all these pictures on the board at the same time. Because our truth tables are very small. Places where we would actually use the truth table, like putting together big complicated circuits where we would confuse ourselves without it, the truth table would probably take up this whole board if we wrote really small. So we're going to look at some smaller ones. So for example, a not. We'll start with the not gate. That's our simplest one. Typically, when programming, the symbol we use is the exclamation mark. And it just means negate the value. Kind of like we use not in normal English, right? To go from does to does not, is to is not. We just negate what that means. And in binary, that's just one or the other. So it's a gate that only requires one input and immediately gives us an output. So our inputs could either be a 0 or a 1. And at any point we could think of other things, right? We could say a true or a false, yes and no, up and down. There's different ways we could think about our binary states, but again, 0 and 1 are the easy symbols to write. Just sometimes we're going to use different words to help make sense of our situation. And if we negate it, then not is just the other one. And so that's what a truth table is. It just lists out all our inputs, all our possible inputs, and the outputs we would get from that input or that combination of those inputs through the logic gate. They'll get a little bit more advanced. So also on an electrical symbol, so that's the symbol we use for programming. When we have electrical schematics, I'm going to abbreviate those words because there's going to be a lot of it. So programming, we usually use the not symbol because we have that on our keyboard. And when you see this on schematics, it's a triangle with a little circle afterwards. Just thrown in there. So on a big complicated wiring diagram, when you see that, that just means negate the value. That's a not gate. And as far as electrical circuit, these aren't big, complicated, mysterious pieces. What this is, I'll draw a circle. So the symbols I put here, these two lines that are different sizes, that represents a battery or a source of power for direct current. The longer line being the plus side and the smaller line being the negative side. So there's our battery. And this jagged spot over here, that's the symbol for resistance. But I'm going to use it in this case to represent load. So that's whatever we're doing with the electricity. If it helps to think about it, think of that as a little light bulb. We want the power from this battery to turn on the light bulb. And the way it's drawn right now, it's always going to be on, right? Because the positive side of the battery come over, hooked up to that light bulb, flows back around to the negative side of the battery, and we have a complete circuit, so that's always on. So what a NOT gate does a NOT gate, we put our switch over here and make a short to ground. Electricity is so common in our modern world. There's a few phrases that I'm pretty sure you've probably heard, such as electricity is always trying to find the shortest path to ground, or electricity takes the path of least resistance. So our load, whatever we actually want to do with that electricity, that's going to have resistance. But if we just have a switch that creates a short back to ground, when that switch is off, the only path the electricity can take is through that resistance. But if we turn that switch on, then there's a path with virtually no resistance straight back to ground. So that's what a NOT gate does electrically. It's just a short back to ground, which I just mentioned the TI chips all built up from NAND gates alone. If we have two switches to make that short to ground, it's a lot more reliable because we can't accidentally flip that switch, or we can. It's a lot harder to accidentally flip two switches than it is to accidentally flip one switch. So the combination of NOT and would be multiple switches there. Which I guess before mentioning that, I probably should have drawn the next picture. So that's the NOT logical operation. If something's false, we make it true. Not true would be false. Same thing with on and off. If something's off, then not off is on. And if it was already on, not on is off, is the operation we're actually going to perform. Our next logical operation is AND. Typically in programming, the most common symbol to use for this is 2 ampersands. We also have 1 ampersand, which represents bitwise programming. I'll talk about the difference between this one and bitwise here in just a second. So programming, use that. Our symbol for it in the schematics looks like half of an oval, where there's 2 wires coming in one side and 1 coming out the other. And the value of this is both must be true for true output. Both must be true for true output. So in the truth table, we need 2 inputs, which you can see from the symbol here. I'll label them inputs A and B. So like input A, input B, and output. And we need every possible combination of that our inputs A and B could be in, which are binary states. So there's a nice little pattern, which is almost trivial here, but the pattern is useful when we get up to more complicated situations. So I'll go ahead and describe it. So there are 2 inputs. So we have 2 to the number of input possibilities, which in this case, 2 inputs means 2 squared or 4 possibilities. So a good thing to do is check how many possibilities you have, and then do half of them starting in the first column, and do half of that number as one of the options. So like half of 4 would be 2 zeros, and then the other half is 2 ones. And then keep cutting that in half as you go through your input columns. So here we only have 2, so 2 to the 2 squared possibilities means there's 4 possibilities. So half of that gives us 2 zeros followed by 2 ones. Cut that in half, and then on the next one we just do 0, 1, 1 of each as we go down. And then that's a nice little pattern that assures we get all of our possibility, get everything covered, and we don't overlook stuff by just stopping and thinking through. trivial in this case, but when we get to a situation where we actually need a truth table, patterns like that to make sure you don't miss anything are very useful. So the number of possibilities you have, cut that in half. Then half of them are zeros and half of them are ones in the first column. And however many of those you drew, cut that in half and keep cutting it in half for all your columns. So then our output, well, we only get true when both of our inputs are true. Right? I like the analogy of like a court of law. The and is for the truth, the whole truth, and nothing but the truth. So using 1 for true and 0 for false here, the only way we have the truth is if we have only truth going in. The truth, the whole truth, and there's not anything but the truth. Whereas in all of our other rows, you can see there's at least one thing that is in that but the whole truth. They're not the whole truth. There's something false in every other one. So when we apply our and operation, which is inclusive, kind of like we use that in normal English, right? Somebody asks what you want for dinner, or you ask your kids what they want for dinner, and they say pizza and tacos. That means they want both of them, right? They want a slice of pizza and a taco sitting on a plate, not a choice between them. Actually have both of them. So and is inclusive.
The computer would make it a pizza taco.
What's that?
I said the computer would make it a pizza taco.
Yes, which does sound really good. Put pizza toppings on taco shells, or taco toppings on a pizza crust. Both ways sound really good.
Don't get me started on taco pizza. Taco pizza is great. If you've never had it, try it at Casey's.
So that does sound good. So again, what this is in schematic, again, it's not a super big complicated thing. And this one, lots of people have in their houses. I'll draw the whole circuit here. I'm going to erase it. I'll come back and draw this top side. I'll draw the AND gate over there and draw the rest of that same circuit we had over there. So we have some sort of load that we're trying to power from this direct current. And in order to get there, we put 2 switches in series. And the word series means that, well, you can see from the picture, they both have to be on. If this switch is on, but the second one's off, the electricity can't get all the way around. Or vice versa. If this one's off and this one's on, the electricity can't get through the circuit. So if you compare that to our table here, if anything's off, the electricity isn't going to be able to flow all the way around and make a complete circuit. Which those are very, very common for in houses, like a ceiling fan. Okay. But usually on the ceiling fan, you have to have the switch on the wall on, as well as pull that chain on the ceiling fan itself. So both switches have to be on. And combining not and means we have 2 switches on our short to ground, which gives us more stability and less chance for accident than we would have with just 1 switch on our short to ground. And our third logic gate, the OR, it's just like we use in English. Using that same example, if you ask your kids what they want for dinner and they said pizza or tacos, that means either one would be fine, right? You don't have to go and cook both of them or try to combine them and make taco pizzas. But
which is a no-go. You say
Yeah.
like taco pizza, like, unless it's like very good, you
Yeah.
know.
the OR situation is, yeah, exactly like it's that unless thing.
I wish
We don't
computers could
have
tell you. I would.
everything.
I wish computers could tell you how good or bad things are. They can only tell you just the variables like pizza, tacos, and whatnot. They can only tell you that. They can't tell you how good or bad a thing is.
So here with an OR gate, if any input is on, the output is on. So I mentioned, and you can think of the analogy of a courtroom. The truth, the whole truth, and nothing but the truth. So only that one row is going to work. But an OR gate is more like desperate hope clinging to hope, desperately believing that there's some truth in the things you hear. And so again, we need two inputs so we can combine them. So input A and input B to produce an output. And what this is leading to is when we do conditions like those if else thing selection structures we were doing last week, we can start combining them. If one condition and another condition are both true, so we can check more than one thing at once. If condition 1 is and condition 2 are true, or not condition 3 is true, and we can start building up more complicated conditionals. Which, by the way, are symbols for that in programming. Most often is 2 pipe symbols, which you probably have never used. That's the vertical bar shift, and then the key right above the enter key has a vertical bar on it. It's called the pipe symbol. But that's usually our symbol for OR. And for electrical schematics, the symbol for OR looks something like this. Almost like we squeeze down that nice little half oval. Let's see if I can draw that a little bit better. Maybe if I had a big piece of chalk instead of that little bitty. Something like that. 2 inputs and then an output. It's clearly like the sides are smushed in from the and symbol. And our truth table of this, again, our inputs could be either 0 or 1. There's 2 possible inputs, so 4 possibilities we could have. So 2 zeros and 2 ones, cut that in half, and then 1 of each, 0, 1, 0, 1, just for a nice pattern to make sure we don't miss anything. Again, trivial in this case, but in complicated situations where we'd actually draw a truth table, it's easy to miss things if we just think them through try to think them through one at a time. So obviously, if I'll say off, if we have 2 switches, off and off, both of them are off, there's no way we can get an on out of 2 offs. And the other, if there's any input is on, it'll be on. So if this is off or this is on, there's that non-inclusively, we got an on in there, so that would be on. And the rest of them would all be on. So yeah, the opposite of a court of law, where we're just like desperately grasping for any straw of truth we can find. It's like, oh, okay, yeah, that's close enough to a true statement. I'm gonna hold on to that one, despite everything else in the big long paragraph that led to the 3 words that seem true or something. The grasping at straws for truth.
The Chewbacca defense.
Yes. And as far as what this looks like in an electrical circuit, I'll finish that out here in a second. So we have sort of the same thing. We have direct current, which is the type we actually need to do stuff with, like a battery. We want to power some sort of load with it. And one thing we could do is split off into parallel branches and then put a switch on each one of those branches. So that if either one of those switches gets turned on, the electricity can find a route through. If this switch is on, doesn't even matter what the other one's on, can go this way. If this switch is on, the electricity can take this path around the circuit. So that's like your garage or your stairs, the three-way light switches in your home, where they vary depending on which one you're closest to. Right? Stairs are dangerous of trying to go up and down stairs in the dark, so there's usually switches at the top and the bottom, the three-way switches, and we can use either one. Either one of those will turn the light. Will turn the light for the stairs on. So similar to things we have in our house, but that's all it is ways to combine those. The most common combinations are going to be NAND, which is not and combined to give us NAND, and not or combined to give us NOR. And if we combine NAND and OR, we get XOR, which I guess I'll draw that up here. Is it okay if I erase the not side? Everybody that's taking notes, get that in.
Yeah, I
there.
got it down. I got it down. Thank you.
Okay, or get a picture of it. Pictures are nice when we have video.
Very true. And something about this COVID thing. I'll get off topic. Never mind.
It's easy to get off topics. Our other one is XOR, which is exclusive OR. Or I'm going to write it as an adverb, exclusively OR, which I'll just put in the truth table here. So we have two inputs again and an output.
Is XOR and an or NAND and no or?
What's that?
Is XOR and an or NAND? And
NAND and OR.
Okay.
So a NAND is, both of them are on. If both switches are on, it creates a short to ground. So combining not and and. So yeah, I'll draw this out. 0, 0, 1, 1, 0, 1, 0, 1. So it's exclusively one or the other, but not both. So obviously, if everything's off, there's no way we can get anything on out of it. And then this one of them's off and one of them's on, and vice versa on the next row. One of them's on and the other one's off. So they're exclusively or, it's one or the other. But when we have that both situation, we get another off, which is a combination there. The OR gates, 0, 1, 1, 0 from the OR gate, turn it on, and then the 1, 1 from the not and. I'll put an and column right here, because we have our and column. So not and is just the negation on all of these. So from the NAND gate, when both of our inputs are on, we get an off. So that's what those two combine to give us the exclusive OR. So one or the other, but not both of them. That's a pretty common one as well. I was debating on the symbol, because this could lead somewhere else. Programmatically, our symbol for that is a caret. The little triangle thing above the 6 caret, it's the unit for joules. I don't know why that made it on the keyboard and the degree symbol didn't, because it seems like we use degrees a lot more than carats. But yeah, it's on our keyboard. So that's our symbol for XOR. There also happens to be a coincidence, just And it's just a coincidence that when we do XOR on two binary numbers, we happen to get the same thing as if we would have took one of those numbers raised to the power of the other one. So it's just a coincidence. So a lot of times people use that for the exponent operation, the power operation. But that is just a coincidence that happens in binary with exclusive OR. Electrically, our symbol looks like an OR gate. I always have trouble drawing the XOR, but when I'm sketching them out, or I always have trouble drawing that OR symbol. But if I need to do a sketch, it's usually obvious what it is. And it's like the OR symbol with an extra line behind it is the schematic symbol for it. So that's our basic ways to combine logic. And then a truth table where we list all our possible inputs and outputs, do things. So then we can do more complicated things when programming. There's a couple other things I want to talk about first. I want to do a more complicated situation for a truth table, not something super complicated. But is it okay if I erase the board? Like the whole board?
Yeah, it looks good.
Yeah, so you can see it's really simple concepts too. It's not some strange mysterious thing. The ands and the ors are light switches that you probably have those kind of switches for the lights in your house. And electrical shorts happen sometimes, right? Everybody's probably experienced an electrical short at some point. So they're things that happen around your house. It's just we're using them slightly differently than turning on and off the lights, but not very differently. We're using lots and lots and lots of them is the difference. So for a more complicated situation, let's do 3 inputs. We have inputs A, B, and C. And I'll use the words. I'll use both of them. Actually, since I have an A here, I'm going to write and in lowercase letters. This counters what I said earlier. This is the logical operation and. A and B, or not C, is the one to set up a truth table for. So not a super complicated one, but you'll see the truth tables get fairly large fairly quickly. So as our situations get more complicated, so will this. So we always want to start with our inputs. So we have 3 inputs, A, B, and C. And I saw earlier this pattern. So there's 2 to the 3 possibilities. 3 inputs means we have 2 cubed possibilities, which, well, 8 possibilities. We've seen the number 2 cubed show up quite a bit already this semester. So you probably have that memorized if you didn't beforehand. So we have 8 possibilities. So we'll divide that by half. Gives us a 4. So we'll split up our options for column A 4 at a time. So 4 zeros and then 4 ones. Again, this is just a pattern to help make sure you don't miss anything. Then we'll cut that in half. 4 divided by 2 means we need 2 at a time in the next column. So we'll do 2 zeros, 2 ones, 2 zeros, 2 ones. cut that in half. We need things one at a time for our third column. So just a nice little pattern to follow to make sure you don't miss anything. Well, we could jump right to the end here, but typically what we do is start making more columns to do the combinations. So as we look through here, there's several parts. We have A and B. Not C would be done first, and then we'll put those two parts together. We'll talk about order of operations here in just a moment, because it's actually the same order of operations you know from your regular math class. It's just not easy to see at first, or if you're not, you were probably presented order of operations in a way that made it easy for what you were doing instead of the full actual process for it. So first thing I'm gonna do is do a column for not C, which is easy because that's just negating our C's. So all the zeros become ones and the ones become zeros. Then we can do a column for our other part, A and B. So I'll use the symbols this time. Typically in programming it's 2 ampersands. So A and B. And 1 ampersand is bitwise operation. So let's say we're working with bytes. So A is a byte, or we have 2 numbers, 2 values that are both stored in bytes. Both of them are 8 bits long. When we combine those with and, we get a 1-bit result. It's either true or false. But a bitwise operation, we would get an 8-bit result. It would go every single bit between the 2 numbers and give us that what each column had in common as far as the and. The same thing with bitwise OR. We can do it bit by bit, and if we feed in 8-bit numbers, we get out an 8-bit result. Versus the 2 ampersands is our regular and, where if we feed in 2 8-bit numbers, we still get a 1-bit result. Usually this is the one we want to work with. So A and B, well, we'll go through the column here. Well, we only have to look at the B column there at the start because all of those A's are zeros, and it's our inclusive operation. So we know our first 4 have to be zeros. Because before we even looked at the second column, well, there's no way we can get an and out of those 4. Then our next one, well, 1, and then we have a 0, so we still can't have 1, 1, 0. Then our last 2 would both give us a 1. And okay, so there's the 2 parts of our more complex expression. So we can combine those into the result of A and B for not C. And we only need these 2 columns to do that. And the OR is the one that actually relates to this column. I'll put those in parentheses, because we already have those. So we just need the OR situation. 1 or 0. What would we get from 1 or 0? Somebody want to rattle off the answer to that?
1.
Hmm?
Yeah, okay.
Yeah. What about 0 or 0?
0?
Yep.
Makes sense,
We
yeah.
already saw that next one. We already saw that one. We already saw that one. I already saw that one. Oh, this one's something different. What do we get from 1 or 1?
That be 0 as well?
That would be XOR.
Oh, okay. So it's
With our
just 1.
regular OR, we'll accept both of them are true. If anything's true there, we'll accept it.
Okay, yeah, XOR is either, but not both. Right.
Yes.
Okay.
I
So
think
that
my
was
line's got off
reasonable.
somewhere here. Down to one would be one.
Mine definitely have, and I'm using lime paper, so don't.
Okay. Oh, yeah, lines are helpful. Yeah, or an OR gate is like this, the light switch on your stairs, right? It doesn't matter if you turn it on from the top or the bottom. If one of those switches is on, you can see to get up and down the stairs.
It goes straight to the ground to flip
Yeah,
the bit.
and if both of them are on, then the light's on. 0 and 1, we already, that or 1, there is an on there, so we'll go ahead and accept it. So that's where we would use the truth tables. You can see the pattern just could build straight up from that and get fairly large fairly quickly. Because every time we add another input, we have to do twice as many. Because if we had 4 inputs, there'd be 2 to the 4th possibilities, or then we'd be to 16 rows with 4 inputs. With 5 inputs, would be up to 32. So the truth tables can get very large very quickly, and in those situations, it's hard to keep track of this stuff. So that's where it's useful, but the homework questions are going to be, any homework questions you'll have will be kind of like this at the most. Most of them are going to be the simple cases, like what's an OR gate look like, and you'll draw those 4 rows for an OR gate. It scales directly up. Does that make sense? See how that could be somewhat useful in big complicated situations where we have lots and lots and lots of 1s and 0s that aren't relating back to numbers that we have to keep straight.
Yeah, it helps us organize them. And the tables.
So next thing on the notes, I threw in something that somebody asked earlier this semester. Yeah, is it okay? Ever go ahead and erase the board? More pictures. What time is it? It's 1:53. Okay, get right on that. So yeah, that's how we use truth tables to organize our thinking. Obviously, we could sit down and keep the situation entirely in our head. We're humans, we're intelligent creatures, we remember things, but we're also humans. We're prone to making mistakes, right? So that's where the truth table comes in as a useful tool. So the next thing I wanted to talk about, a question was asked earlier about memory. I think it was this class, but 2 NOR gates make a bit of memory. In particular, DRAM. There's the cheaper SRAM. It's cheaper, but it's more temporary. And what that entails is basically a transistor, which I'm just going to write as a switch here, that feeds into a capacitor, which is a little piece that can hold a charge. If like your spark plugs in your car, there's a little gap there between things. So as electricity tries to flow through it, it builds up and builds up and builds up until it's enough to actually jump across there. If we stop right before that jump part, then it builds up and builds up and builds up and just stays there until we release it. Obviously that's really, really cheap, easy to make, but it dissipates on its own. A few minutes at most. So we put SRAM in there, it's really cheap, and then just add a refresh in it so that whatever's there, if it's charged up, it's holding a 1. If it's drained, it's holding a 0. Oh yeah, and then another's a full circuit, so it gets back to the ground and can drain. And then we just every couple minutes or a few seconds, we just look at what's there and put that same thing back in. So there's some overhead in using SRAM as well, but much cheaper to make. The DRAM, the better kind, it just involves 2 NOR gates. I'll draw like this. So that little dot, well, I'll draw the whole triangle. That's what we saw. So we have an OR, and then we knot that OR. And we do that twice. So an OR gate, and then we run that through a NOT gate. And the output of one of them comes down and feeds into the other, and vice versa. After we output it, it'll come over, jump over that wire so they don't touch, and feed in there. Then we have another one that's just always tied to 0, just always stays as a 0. And then we have our actual input. So first, everything's going to have zeros, right? I'll put a 0 here. Which makes, well, ultimately a 0 is going to come out of there. This has a 1 on it. We'll get there in a second. The 0 come, so 0 and 1, not OR would give us a 0, which feeds a 0 in here. We get a 1 out here, which comes back up here. And if we switch that, maybe I'll try using a different color. Then if we put a 1 in there, 1 or 1 would give us a 1. Wait. We have zeros everywhere, right? Yeah. Let me go back a step. So we have a 0, 2 zeros going in. Initially, everything is off. So 0 or 0 or 0 would be 0. When we negate that, we get a 1, which sends a 1 down to this line. 1 or 0 is a 1, which gives us a 0 out here, the same as the 0 here. So this output down here has the same thing as our input. And if we switch that and send in a 1, then we have 1 or 0, which would output a 1, but when we do not that, we get a 0, which then sends a 0 down here, and we have 0 or 0 comes out as a 1. So we have a 1 on that same output. So this output down here always has the same thing as what we send in. And when we set up memory that way, it'll stay there for as long as the computer has power. Then once there's no longer power, we can't possibly have any 1s there. So everything goes back to, gets erased. And that's the volatile part of memory. It's only there as long as the machine has power. Once we shut it off, it has
And SRAM is based off of stored power, so that's why it's not as effective.
yeah,
Stored
because
in the circuit
yeah,
on
it's
buildup.
it's stored power, which coming around, yeah, I'll draw it like this. Would eventually come back to the ground. We turn it on, our charge builds up, and we have a charge there, but there's always some resistance. Like the wires that leading through there produce some resistance, which means those wires are basically going to use the electricity that's stored there over a few minutes time, even if it's shut off. It'll kind of dissipate into it. So we have to constantly refresh that. Or we just, it's actually an isolated thing. Then we have, it actually looks more like that. So we have 2 switches. So if we want to put something there, we close this side and fill it up. If we want to take it out, we close this side and let it drain back to ground really quickly to get our 1 or 0. So less pieces, so easier to make, cheaper, but more temporary. This one will last as long as power is supplied, and this one will fade away. Unlike some of our other types of storage, like magnetic disk drives, where we can adjust the polarity, or magnetic tape even before that, we can adjust the polarity of the magnet and then have the North Pole or South Pole represent something. And then it's a magnet. It doesn't rely on electricity. So if we turn the electricity off or on and off 1,000 times,
So that's how long term storage works.
Mm-hmm.
How's that work? Okay, might get off topic, but how does that work with SSDs then? Because okay, I know they're DRAM. Is there a specific way that they're less
SSDs
volatile?
are actually storing charged particles. So we set it up like a big grid.
So they have like little batteries, basically little tiny little, not
Yeah,
batteries, but
yeah,
little
and,
power sources.
So not even like that. So some of the grid have extra electrons, and some of them are missing electrons. We could say it that way. Negatives are ones and zeros. And
Oh, okay.
There's this thing from quantum mechanics, which it's quantum mechanics, so it doesn't make a lick of sense when we try to put it in English. So the math equation works out. We're willing to risk lives on the math equation being correct. Doesn't make a lick of sense in English though. But when we have these set up, we can flash certain electrical conditions, and then these electrons that were here appear over here somewhere else.
Is that because it's superpositioning? Like,
I
might be
positioning. It's tunneling.
tunneling.
Yeah, Fowler-Nordheim tunneling.
It's fascinating.
There's a barrier that they can't flow freely across. Electrons would try to do that. So if we set up the conditions exactly right, they'll appear over here, which is where it gets really confusing because they don't move between there and there. They were here.
They just appear.
Then they're here, and they're never anywhere in between.
Okay.
The math equation, it's a really complicated math equation that when we plug in values, we know it will always be correct. But that's what solid state drives do. So they do something a little bit different, but they're based off ionized particles. So the ionization is a chemical process. It will remain there.
Okay. So and that's why they're not permanent,
Yes.
because that ionization will dissipate eventually.
Yes. And since we're talking about this, might as well go. So with the explanation, the question popped up in the chat room about on the silicon, how that works. So yeah, this is a good place to address questions because we're almost ready for an example on this stuff. And these are things you've probably been curious about. So silicon is an element. I'm going to go with the simpler Bohr model. Y'all may have seen this in, this is the one you've probably seen. That's the one where we have that nice little nucleus with all the protons and neutrons in it, and then electrons and nice organized orbits around it. We know it's physically inaccurate, but it helps to make sense, and it's good enough. It's good enough for explanations a lot of times. And the electrons go in nice little orbits, and this one would have 4, so we have 2 there. All right, face around. And our third one, our third orbit, if we look at this model from chemistry on silicon, well, the third orbit should be able to hold 8 electrons, but silicon only has 4 in that outer one. So it's exactly half full. So if it encountered another silicon atom, and on this one, I'll just draw that outer shell. Another silicon atom is also exactly half full. So both of them are, they need 4 more electrons to fill up that outer shell. And they'd be just as happy to give away those 4 electrons as they would to take one from another atom, because then they're, either way, they have their outermost shell full. So if one of them gives up their electrons to go over to the other one, like say this one, those electrons move over here. And that one has a full outer shell. And then this one was, well, its outer shell is empty now, so the next shell down would be full. So both of them are in a stable state. But that changed the polarity because none of our protons moved. So this one has more electrons, so it's negatively charged. And this one has more protons, so it would be positively charged.
We can assign 1s and 0s to that.
Mm.
Okay.
Yes, so then we get that, we get the polarization between them, between silicon. And it creates a really nice balance on everything. So then actually what we do is we mess up that balance. We get pure silicon, and that's the hard part. That's the thing that you couldn't do from scratch, because the pure silicon, you have to have a clean room to work with that, and clean rooms, the cost for a clean room starts at several $billion. So there's lots of other ways, bigger components we could use and stuff, but actually using the silicon, we have to build up $billion clean rooms so we have very pure silicon, because then we can introduce other things. Phosphorus and potassium are the most common to dirty up that balance. We can mess up that balance with some things that would use some of those, that would want some of those other electrons. Which one? Potassium. I think I have to look at a picture of the periodic table. Make sure I draw this right. Which I suppose I could share my screen while I'm doing that, huh? Obviously an easy thing to find. So potassium is over here. It only has 1 electron in its outer shell. And phosphorus is over here. And if you haven't seen this in the chemistry class, as we move left to right on the periodic table, the outermost shell fills up. So this has all but 2. So this has 6. 4, 5, 6. So phosphorus needs 2 electrons. Potassium needs 7 electrons. Which means potassium is very likely to give off that extra electron. Which means there's an extra one. If we add potassium into our nice pure silicon, we mess up that balance because there's suddenly extra electrons floating around. Or potassium only needs 2 electrons, using the Bohr model here. So it's a lot more likely to grab 2 electrons than a silicon atom is to grab 4 electrons, which again messes up that nice little balance, only in the opposite direction of potassium. So then we end up with polarized things. And when we can combine them, we put them right next to each other. Those extra and missing electrons kind of filter in at the edges. And we get some polarization that we can then control. It's kind of how that comes about. Did that answer those questions? Kind of address that, or at least start you down that direction. Obviously, that gets to be a very complicated thing. There's a lot of chemistry and physics involved. But we have this nice little balance that the element silicon wants to do on its own. So if we have absolutely pure silicon that will try to do that, and then we mess it up in a very organized fashion so that we can control that balance afterwards. Which then it just so happens that produces physical properties that we can control by the shape of it. If we look at the edge of a silicon wafer, it can only exist at certain angles.
Is that
And
where traces come from?
what's that?
Like traces on a motherboard? Is that okay?
Oh, well, the traces on the board are just copper. They're pieces of copper laid down. This is the black, well, this is what's inside of this little IC I grabbed.
Oh, okay.
If you cut one of these open, this is mostly black plastic to make it big enough for our fingers. Inside of it, you'll see something that looks like glass.
Huh.
Silicon is how we make glass.
Yeah, and
Silicon bicarbonate would be the technical term for glass. So if you cut this open, you'll see a little purplish thing that looks like glass. There's no carbon in it, so it's softer than glass. But if you have an old IC, cut it open and the silicon stuff's inside of there. And then it can only exist at certain angles, and we can control the angle we cut it at or etch it at. And then that angle happens, those angles correspond to one of these situations directly. So we just adjust the angle at the edge of the silicon. There's only 3 possible ones. So when we cut that silicon wafer, actually we use acid to burn it away. Depending on one of these situations, it can only be at 1 of 3 angles, and that gives us absolute control over it. But that has to be done in a $1 billion clean room. And several $1 billion for a clean room is just like the starting price on them. That's the thing that can't be done, right? Plugging up our circuits and messing with magnets, we can do that with our hands. So the concepts are there, but this one gets a little more complicated and you have to get into chemistry and physics, and solid state drives actually require some quantum mechanics calculations. So it can get very advanced, but does that sort of fill in some of those gaps?
Oh,
Start you on that path of learning these things.
thank you.
Yeah, again, I use the simplified chemistry model. There's a more complicated one.
It helps differentiate, like, SRAM from DRAM and like the flash state of solid state drives. Thank you for helping me understand that.
Yeah, the solid, so that's our solid state, which it comes because of that flash we give it, which makes the stuff jump to a different spot in the universe.
That is your turn too, like why we call it flash storage. So that's
Yeah.
that. The
And then
moving
you
of
have a spinning, well, I'll use a spinning disc with a bunch of north poles on it, and then we have a little magnet that sits on a spring. So as that disc spins around, it's going to push the north poles away from it, and whenever it's above a south pole, it would pull it towards it, or vice versa, depending on how the magnet's polarized. Same thing as the tape drives. With 2 pieces of Scotch tape with a bunch of iron filings between them, so they're oriented either north or south. So if we run them past a magnet that sits on a spring, that magnet bounces up and down, and we can tell whether there's a north or south polarized thing in the tape. And if instead of letting the magnet bounce, we hold it still, then we can change the polarity in the tape or the spinning disc. So that's how the different types of storage compare. Any other questions while we're off on a little tangent like this?
continuing with the magnetic tape, that can be the same for like with 8-track, right? Same.
Yes.
Okay,
Yeah, the
cool.
audio tape evolved from this.
Huh.
Because
really-
yeah, then we instead of doing one or the other state, right? The magnet there is really a small piece of audio or a bunch of iron filings. So we have a bunch of iron that's polarized, so each piece has a north and a south magnet. So on a computer, we would turn them very definitively. We have one or the other, but we don't have to turn that all the way, right? We could turn it just part of the way and then get different effects from it. So the
Yeah.
audio tape,
The sound wave. Exactly.
yeah, based off the sound wave, we would just partially turn that magnet instead of fully.
That's really cool.
And then, yeah, and then it's organized, you know, it's a little bitty small thing. So we could put, well, 8 tracks, we could put eight magnets next to each other on the width of it, the width of that piece of tape.
And that's why it's called an 8-track.
Yep. 8 separate tracks on one piece of tape. Which also works really nice for computer code too, because then we can do 8 bits across instead of just 1 bit lengthwise on the tape. Yeah, this class often gets little tangents like this. If you have some questions, we can go off on these tangents, because I remember being curious about all this stuff myself, and I've been looking into it for a very long time. And yeah, it's nice to hear answers to the questions, make sense of what they're doing.
It really is. I appreciate like being able to understand it at a deeper root than just, oh, it works, you know? So thank you.
There is a playlist on my YouTube channel that was just addressing questions like this, because I noticed when things first went virtual, nobody would ask them. Everybody would sit there quietly, and it's like, okay, every time people ask the same questions, I can make a bunch of videos for this. It also has like touch screens and how transistors work versus the old
Or like pressure versus heat.
heating coils. And yeah, so I have a bunch of videos, which I put the link to that on everywhere somewhere. So one last thing I wanted to draw on the board before we get to examples. We talked about that 2's complement being the only operation we need. So let's take 2 numbers, 10 and 3. There's that 1 0 1 0. Saw that, and 0 0 1 0. And 2's complement would be the only operation we would need to combine those 2 things. And how that works is our combination is an XOR and our carry bit is an AND. Because what's 0 or 0 will give us a 0, right? And 1 XOR 1 is how much? This is the one you were thinking of earlier, Tyler. 1 or 1 would be true, would give us a 1, but it's not exclusively. So that would give us a 0 for the XOR, but 1 and 1 would give us a 1 for the carry bit. And then actually we need 2 layers of that, because we have to check this result with anything carried from the previous column. And again, 0 and 0 XOR 0 is going to be 0. But then when we XOR that with another 1, we get a 1. Just like we were doing the other day, 1 plus 0 gives us a 1. 1 plus 1 gives us a 0, we carry the 1. So XOR on that is a 0. And on that is a 1. And this last column, 1 XOR 0 was exclusive or. It's one or the other, but not both. So that gives us a 1 there and a carry. Oh, that's a 2. I meant to write a 3 and wrote a 2 instead. And then we carry 0. So that's kind of how the circuit works, is just a combination of these gates is how we do all our math. And then we already saw how we can do that works for 2's complement, and both 2's complement for add the negative or for adding two positive numbers.
So that's how we can get two's complement on a hardware level.
Yes. Yep.
Okay.
It takes a lot of wires. There's a video of that in that video playlist I just mentioned on my YouTube channel. Something about removing mystery. There's a link to it in Ivy Learn. I built one of those, but I only built 2 columns, and the spot where you see, oh yeah, 2 columns in this, where you, if you check that video for how many wires it took to put 2 columns together, you'll see why I only built 2. The pattern continues, but it takes a lot of wiring to get it. Much easier to draw the picture on the board. Okay, so, but essentially, the reason I wanted to go off on those include those things is to show that these logical operations are the only ones that we need to do all of the computer stuff. Yeah, then all that was the physics and chemistry to address questions and hopefully satisfy some curiosity on how these things work, because you probably would have just heard bits and pieces along the way. One more thing I wanted to cover before an example, but it's probably a good time to take a break, right? We've been at this for a minute. That was a lot of information. We related this to math, right? So there's a Boolean algebra. So this stuff is an explicit math form, which means there's an explicit order of operations we need to follow, just like when we do our addition and multiplication. And it's actually the same order of operations, but we have to re-examine the ones we know to get there. So it'll take, we can do that after a break. It's probably a good time to go grab a cup of coffee or something first, right? Does 10 minutes sound good to everybody?
Sounds good to me.
All right, so it's 2:23. We'll get back to it at 2:33 with order of operations, and then we'll jump into some programming examples to see the ands and ors and nots worked into our selection structures. I'll see y'all in a moment.